presentaciones, en mis slides, tomo unos de esas slides en el cual el profesor Mario Reis hace un resumen en una sola figura de todos los tipos de magnetización que hay en las gráficas, susceptibilidad versus temperatura y susceptibilidad versus campo magnético. Cuando yo era estudiante me hubiese gustado tener esa gráfica, nunca lo tuve y lo encontré recientemente en un libro publicado por el profesor Mario Reis. Bien, es un honor tener al profesor Mario Reis aquí. A los que recién se conectan, bienvenidos a la red latinoamericana de física de materia condensada y ciencia de materiales. Welcome to the network of matter condensed physics and material science. Well, very shortly, Mario Reis, I will introduce you very quickly. I introduced you some people, but there are also some invited panelists. Professor Delian Zhang, who has already connected, who is the editor-in-chief from the journal Heat Treatment and Surface Engineering. Delian, can you show your camera, please?
Oh, hello, Luis. Hello.
Yeah, Professor Delian Zhang, the speaker today is Professor Mario Reis, the author of the Fundamental.
Hello, Professor.
Yeah.
Hello, nice to meet you.
Yeah.
Nice to meet you.
Good morning to
Also,
everybody.
let me introduce you, Professor Albino Aguiar from the Federal University of Pernambuco in Brazil. Yeah, Professor Albino Aguiar is also one of the invited panelists. Dr. Peter Newton from the University of Cambridge.
Hi, good morning, everyone.
Yeah. Felipe Mundaca from the University of Puerto Montt in Chile.
Good morning.
Professor Albino Aguiar, University of Barranca in Peru.
Hello.
Professor Arturo Martinez. Professor Arturo Martinez from the CIMBESTAP of Mexico.
Good morning.
Professor Felipe Mundaca, yes, already told you that from the Puerto Montt, Chile. Professor David Landinés Telles from the National University of Colombia.
Hi, morning.
Professor José Fermín from the University of Zulia in Venezuela. Yeah. Well, okay, now today the Professor Isaías Gonzaga de Oliveira from the Federal Rural University of Rio de Janeiro will be the moderator, okay? Thank you very much for your attention. Isaías? Your microphone, Isaías. Your microphone is not working, Isaías. Well, we need to mention, while Isaías is connecting his microphone, we need to mention that the official journal of these seminars is Heat Treatment and Surface Engineering from Taylor and Francis online. Okay, Isaías? Well, everybody is invited to submit your articles to this journal. Okay. Isaías, are you online? No, doesn't work. Okay. Well, I will continue then introducing you, Professor, some part in Spanish, okay? Profesor, toda la comunidad latinoamericana, el profesor Mario Reis, es el autor del libro Fundamental of Magnetism y tenemos el agrado de tenerlos aquí en esta red conformada por la Universidad Nacional Mayor de San Marcos en Perú, Universidad Nacional de Barranca en Perú, Universidad Federal de Pernambuco en Brasil, Universidad Federal Rural de Río de Janeiro en Brasil, Universidad Nacional de Colombia en Colombia, Universidad del Norte en Barranquilla, Colombia, Universidad Puerto Montt en Chile, Universidad de Zulia en Venezuela y toda la red latinoamericana. Perfecto. Perfecto. Entonces vamos a empezar. Mario Reis, puedes compartir tus slides y empezar tu charla. Mario Reis, you can start your talk now.
Okay, thank you. Can you hear me properly? I think you can, right? Because you were talking before.
Yeah.
Okay,
Yes, we
great.
can hear you and you can start sharing your screen. Al público pueden ir dejando sus preguntas a través de las redes sociales donde están siguiendo esta transmisión.
Okay, but I think I cannot see the questions, right?
Yes, you can share your screen.
Okay.
It is the green button on the bottom.
Yes, just a second, because I'm using a Mac and she asking for rights access.
Ya, access. Claudio Donicio, por favor, accede, darle la que Mario Reis pueda.
Okay, it's a small problem here because the system asks to restart the browser.
Okay, we can wait for you. No worry, we can wait.
Can you hear me now?
Yes.
Oh, thank you.
I don't. It's an option to later. Let me see here if it works. Can you see if it's shared or not?
Not yet. Flavio Donicio, permitir que Mario Reis pueda compartir su pantalla, por favor.
Let me try again.
James, ¿puede
Share.
permitir? Okay.
Okay, but it's shared.
Yeah,
Yes.
yes.
Okay, great.
But it's not in. Okay, now it's okay.
Okay.
Perfectly.
Okay. So, first of all, it's a great satisfaction to present this talk for this network. I'm very surprised with this organization. I entered the website of this network, and I saw several interesting topics covering several different fields about magnetism, and with different researchers from Latin America and even different countries out of Latin America. It's a very well organized network, and it's a satisfaction to present this talk. And thanks for the organizing committee to invite me to present this talk. Well, for today, I'm talking about the caloric effects about metal complexes, and it's a topic. The caloric effects. The magnetocaloric effect, it's a topic that has been studied for the community of magnetism for several decades. And the barocaloric effect is a new effect it's a not new effect, but for the magnetic for the community studying magnetics, it's a new topic that has been aggregated to this effect. And this community is studying the caloric effects about these magnetic materials. And I'll focus my attention today to the metal complexes. And for today's talk, I will present the goal of the talk, two surveys, one about metal complexes, another about caloric effects. One survey about metal complexes, another about caloric effects, and then two descriptions about these connections. One, the magnetocaloric effect of these materials at low temperatures, another, the barocaloric effect at room temperature. These two are completely different physical mechanisms, but these two are related to the same material, the metal complexes. All of the ideas I will describe along this talk are described in this review article I have published 2 years ago. It's not a pretty new review, but you can find the main ideas here in this review. For those researchers, colleagues that are interested to go deeper on the subject, students, change the fields, it's interesting to start with a review. And I suggest to start with a review, and it's going to be a first step. Okay. Well, how can I start this talk discussing physics? I will start this talk discussing the properties of the material, the metal complexes. Let's see first this periodic table. Metal complexes can be constituted with two kinds of metal centers. Transition metals, like usually from manganese to copper, like here, manganese, iron, copper, cobalt, nickel, or copper. These are the standard transition metals for these materials, or rare earths, usually gadolinium when the material is made for magnetic applications, europium for optical applications, and also other kinds of rare earths. But these two are very common, gadolinium and europium. But to summarize the idea, rare earths and 3D metals. However, there isn't metal-metal bonds. Usually, the bonds, the chemical ligation, the chemical connection is metal, sp ion like carbon, nitrogen, oxygen, even fluorine, and then another metal. And this bridge, like metal, sp and metal, is very important. And the angle along this connection is very important for the magnetism of the material. There are several coordinations that can appear for these metal complexes, like this one here on your screen. These other kinds of coordination. Square pyramidal, like this one, square planar, like this one, and the octahedra environment, the octahedra coordination, that's very important, including the discussion I will place for you at the second half of this talk. In terms of magnetism, we can describe these materials. Let's focus as following. Let's focus our attention to these two tables here. On this left table, we can find a description of a standard ferromagnetic material, like a piece of cobalt. And on the right table are molecular magnets. Molecular magnet is a class of materials inside the molecular magnetism approach. Okay, so it's a special class of materials, and you see why. We can compare both of these materials. Standard ferromagnetic materials, these have 3D cooperative magnetism, long-range magnetic interactions. Let's think about a piece of cobalt, a piece of gadolinium, for instance. Okay, because of the long-range magnetic interaction, these have also phase transitions, because the phase transitions is a consequence of the long-range interactions, and consequently, spontaneous ordering. Okay. And for most of the cases, for these cases, magnetic hysteresis. Okay, it's a standard magnetism, standard ferromagnetism. However, for the molecular magnets, these materials presents a non-comparative magnetism, and it's very important at low dimensionality. I will present some pictures that will make this more clear. It's very important. A non-comparative magnetism. It means that one molecule does not interact from the magnetic sense with the first neighbor molecule. It is a short-range magnetic interaction inside the molecule, because inside one molecule does not interact, magnetically speaking, with the first neighbor. And inside the molecule, it has magnetic interactions. However, these are of short order interaction. Consequently, these materials do not present phase transition. It does not present a critical temperature. However, in spite of that, this presents spontaneous ordering. I mean, the molecular magnets. It presents spontaneous ordering. However, because a quite high magnetic anisotropy. It's quite common, this magnetic anisotropy, in materials with cobalt, manganese, iron. Okay? And consequently, it has magnetic hysteresis even without critical temperature. However, I'm discussing the molecular magnets. Okay, it is usually named as single molecule magnets or single ion magnets when it's the case of a molecule. When it's the case of ion, it can be a single ion magnet. When the anisotropy is quite high for one single ion, and it behaves like a magnet, the single ion, because of the magnetocrystalline anisotropy. However, there are some exceptions. When the magnetocrystalline, there isn't magnetocrystalline anisotropy, and the system is only of low dimensionality, as the case of copper. Because copper, in certain cases, is a D9 electronic configuration, and the spin is 1/2, and spin 1/2 cannot suffer a magnetocrystalline anisotropy. And for these cases, and several others, even for cobalt, cobalt, iron, for some cases, this cannot suffer magnetic anisotropy, and this can also be an exception for molecular magnets. It cannot be a molecular magnet. Can be or cannot be, depends on the intensity of the magnetic anisotropy. For this case, without magnetic anisotropy, we only have a system with low dimensionality. And then we have all of these cases, we have the molecular magnetism. That includes the molecular magnets and systems with low dimensionality, like clusters, chains, etc. I will present some pictures to make this explanation clearly. This picture here is the manganese 12. This material has been quite studied in the literature. We have 12 ions of manganese, 8 ions in this crown here, and 4 inside in a core, 8 with spins up, and 4 with spin down. I'm presenting here only the molecule. The first neighbor molecule does not interact magnetically, as I said, with this one. All of this magnetic description is came from this molecule. There are several articles that researchers could remove from the structure, the chemical structure, this molecule, and deposit in a thin film. And considering the magnetic interaction is of short range, the magnetic properties remain. Okay. Here is the hysteresis that I mentioned before, because of the anisotropy of the material. Okay. Here is another case. However, it's a zoom out from the previous molecule. It's another material. It's another material. Okay. However, here is a dimer. It's a dimer. You can see here these 2 ions here in green, olive, to say more correctly, in this olive color. These 2 are ions of, depends, here can be manganese, iron, copper. You can see these 2 can be manganese, iron, and copper, and in spite of that, these 2 do not present magnetic anisotropy, even considering manganese and iron. You can see here it's a sea of dimers. It's a sea of dimers. And this dimer does not interact magnetically with this other dimer. And to make a description of this material, we want to consider the dimer. Okay, because it's a sea of dimers. Here is a chain for inside this octahedra. We have a manganese. You have a zigzag chain of manganese. It's a true realization of a one-dimensional chain. Here is another example. Here, inside this octahedra, it's a linear, not a zigzag as the previous case. That's here on the back. Here, it's for this case, a cobalt. It's a cobalt chain. Here, you can see for this zigzag chain, the connection of the octahedra is very different from the connection of this octahedra here. And the structure of the material is very different. And it makes different the magnetic properties of the material. Okay. Well, these are general aspects for the materials. We can see, in addition, on the top of these properties, we can add some other filters for the molecular for these materials. These have low density, mechanical flexibility. If you have in mind a piece of metal, even a piece of oxides, you can see the difference considering metal complexes. These have mechanical flexibility, synthesis at low temperature. To prepare, for example, an intermetallic material, we need to produce in an arc melting device, an arc melting furnace, at 200, 2000, 3000 degrees of temperature. Here, these materials can be produced at 200, 300 degrees. Low toxicity, compatibility with polymers and other biological systems, and a lot of properties that make these materials, in fact, very different in comparison with metals and other standard magnetic materials. Okay. Well, here, just to finalize this simple, brief introduction to metal complexes, it's only an example how to prepare simple models to understand the properties for this material. Here we have a chain, a zigzag chain of copper. Copper depends on the electronic configuration. For this case, it's a D9 electronic configuration. It has spin one half. And you can see here, this zigzag chain has a minor block. This minor block is a trimer, dimer, etc. And then we can produce a model considering only this dimer and trimer. The trimer has spin 1, 2, and 3. Because of the angles here inside the trimer, we call J1 inside the trimer. So spin 1, 2, and 3 with magnetic interactions, J1. Because of the different angle inside the dimer, it's a J3, the interaction inside the dimer. And then the effective spin of the dimer, SA, interacts with a J2 with the trimer. It's simple, the Hamiltonian for this system. What's the size of this Hamiltonian? It's a spin 1/2. Spin 1/2, the size of this Hamiltonian is 2, 4, 8, 16, 32. 32 by 32. It's a relatively small matrix. It can be done by hands or using a routine to diagonalize this Hamiltonian. And you can obtain the eigenvalues, partition function, and thermodynamic quantities. It's relatively simple to understand the thermodynamic properties of the material. And here, I can present the susceptibility times temperature as a function of temperature, and the corresponding fit. And the three parameters are the exchange interactions, those exchange interactions, J1, 2, and 3. These are the three parameters. Okay, it's a simple understanding, a simple model to understand how to handle with these materials. Okay. Okay, I concluded here the first survey just to introduce these materials. And considering, I know the community for today, it's a community of magnetism and condensed, not only magnetism, it's condensed matter, but probably most of you already heard about caloric effects. But I think it's important to introduce these effects, at least with a couple, not a couple here in this case, but some slides, considering some students can be in the audience, and it can be new for some students. And what's the main idea about caloric effects? I'm describing the magnetocaloric effect. That's intuitive, but it can be extended for other caloric effects, such as barocaloric effects. It can be understood based on two processes, the adiabatic process and the isothermal process. The one on your screen is the isothermal process. Let's apply a magnetic field. The magnetic material inside, in contact with a thermal reservoir, expels heat to this thermal reservoir, keeping the temperature with the same temperature. When we remove these magnetic fields, the thermal reservoir absorbs heat from this thermal reservoir, keeping the temperature constant because it is isothermal. Isothermal, it's the same temperature. Okay? It's one process. These amounts of heat exchanged with this thermal reservoir can be characterized in our lab. We know this temperature. If you know this temperature, there is one very useful thermodynamic quantity that is the amount of heat exchanged is equal to the temperature times the change of entropy of the system, the total entropy of the system. However, there is one important point that I will describe in a couple of slides ahead. Considering the lattice entropy does not depend on the magnetic fields, this total entropy is the same, will be, for this case, the same as the magnetic entropy. So, the quantity that characterizes the magnetic, these amounts of heat exchanged is the magnetic entropy change, or the isothermal entropy change, as can be also said. There is another potential to characterize the caloric effects. For this case, I'm describing the magnetocaloric effect. I'm considering here magnetic material. The magnetic material is isolated from the environment. It's in a chamber with vacuum. When we apply a magnetic field, the temperature increases. When we remove the magnetic field, the temperature decreases. And the amount of temperature that changes is the adiabatic temperature change. This amount of temperature characterizes this potential. Okay, it's another way to see this caloric effect. However, you focus our attention to the isothermal entropy change. Okay? Based on these two potentials, it's possible to make several thermodynamic cycles. One very common cycle used for magnetocalorics is the Brayton cycle. Here is the entropy as a function of temperature, two curves of entropy with different values of fields, 0, for example, and another curve with different value of fields. The Brayton cycle is based on two adiabatics here, step 1, 2, and 3, 4, and two isofields process. I have here one YouTube video, but it's in Portuguese, explaining all of the cycle, step by step, all of the process, how can remove heat from one side and expel to the other. People that are interested in this, to go further in this topic and understand, can access this video to understand. But it's out of the scope for this talk for today to explain here in details. But it's available to understand. This picture is very important to understand the next section of this talk. Here's the entropy as a function of temperature. These are the main contributions for the total entropy. Here in green is the lattice entropy. In blue, the spin, the magnetic or the spin entropy. And in red, the total entropy. The magnetic entropy, I mean the spin entropy, there are two contributions. The lattice entropy before go further, the lattice entropy has only one dependence, temperature. It does not depend on the magnetic field. It's a Debye, for example, it's a Debye contribution. For this range of temperature, it is like a T⁻3, okay? And the magnetic or the spin contribution, we have here two contributions. One with field, for this simulation is 2 Tesla, and one without field, a zero field contribution. For a higher temperature, it goes to logarithm of 2J plus 1. J here is the total angular momentum. It can be S, depends on the material. For gadolinium, for instance, it would be S, 2S plus 1. Okay? And then the total entropy is the sum of the lattice contribution and the magnetic contribution. Okay? However, the entropy change, the total entropy change, is the magnetic, the total entropy change is the total entropy with field minus the total entropy without field. However, the lattice contribution does not depend on the magnetic field. And then when you make this difference, the lattice contribution is canceled. That's the reason why the total entropy is the same as the total entropy change is the same as the magnetic entropy change, because the lattice entropy does not depend on the magnetic field. Okay, it's very useful, this condition, when you make experiments, because the entropy came from the magnetic measurements is already the total entropy change for this case. One very important point for the next discussion is this length here. You can see that for a certain region, because this length here is the total entropy, or is the entropy change we are interested, that characterize that amount of heat that the material can exchange with the thermal reservoir. Note the following. This length here, for a certain region of temperature, is already the maximum available for the material. It is already logarithm of 2s plus 1. Okay? So, based on this, I can move to the next part of the talk and discuss the magnetocaloric effects at low temperatures for these materials. Here is the specific heat for 1 dimer of gadolinium. 1 dimer of gadolinium. It is from the literature. Okay. Here's the specific heat measured at very low temperature, below 1K, up to 10K, for 0, 1, 3, and 7 Tesla. And here the corresponding entropy, not the entropy change, but the entropy. You see that for 7 Tesla, the outcomes almost reach the maximum entropy change. If the outcomes measured for 8 or 9 Tesla, they would reach the maximum entropy change. What's the maximum entropy change for this material? Here, the maximum entropy change is 2, because they have here 2 ions of gadolinium, R, that's gas constant, because here the unit is R, so the gas constant, logarithm of 2s plus 1. S for this case is 7.5, because gadolinium is the angular momentum of gadolinium, the spin, considering only the spin contribution. And the result is 4.1 R. That's exactly found experimentally. Okay. Now I am presenting here what you have observed, collecting results from the literature that is presented in that review I have presented for you at the beginning of the talk. What we have found collecting results from the literature. Here is the entropy. Here is the time. The time, the year of publication of the article, of the corresponding article, I have found the data. Okay. Here, the first family is only ions or only materials with transition metals, and the average entropy change is around 20 joules per kilogram Kelvin. Okay, and the example is a single molecule magnet. Okay. And the date, the year is around from 25 to 28. Okay. Further in years, the community started to improve the materials and published a mix of transition metal, materials mixing transition metals and gadolinium. And they couldn't improve the average value of magnetic entropy change. They changed the copper, because here is copper and gadolinium. Here's an example. Gadolinium and copper around. They replaced, the community. The community replaced copper by nickel, because the magnetic momentum of the nickel is higher than copper. And then the community increases the value of magnetic entropy change. Further researcher, and around the same years, the community only prepared clusters of gadolinium. And here is an example, a dimer of gadolinium, as I presented before. And in fact, here, these green dots, the average value of entropy change increased. And you can see a further increase on the entropy change, because these yellow dots correspond to chains, polymers, chains of gadolinium. These samples do not contain transition metals, only gadolinium. And the community realized that this is the way to produce materials with enhanced magnetic entropy change at low temperature. I mean, it is at 2K and 7 Tesla. And here, the proposal of the community here is to use these materials for helium and gas liquefaction. Okay. One very interesting point here is the following. Here is an example of the chains of gadolinium. One very interesting point here is the following. These materials here, highlighted with a black circle, all of these follow a straight line. And all of these have the maximum entropy change of logarithm of 2s plus 1. Follow straight line with time. It's like a Moore law for the entropy change. And you can determine a law, let's say like that, as a function of time. And as a consequence, we can say, what comes next? What's the next family here that will maximize the entropy change for this material, for this region of temperature, using molecular magnets, or not necessarily molecular magnets, because molecular magnets are here at low values, but metal complexes, I mean. Okay. Do I have 10 minutes? Do I have 10 minutes to conclude?
Yes, you have.
Okay. Okay, I conclude in 10 minutes.
To tell the truth, you have 29 minutes.
Sorry?
You have 29 minutes.
No, okay, but in 10 minutes I can conclude. All of the discussion I have addressed is for magnetocalorics at low temperature, considering metal complexes. However, these materials are quite versatile, and these materials can present a completely different physics if you study the barocaloric effects, however, in a different range of temperature. The barocaloric effects, the idea is very similar with the magnetocalorics. Instead of the application of magnetic fields, we apply pressure, and the idea is the same. It releases heat for a reservoir due to application of a pressure instead of application of magnetic field. And it decreases temperature due to application of a pressure in the diabatic process. The idea is the same. What's the main mechanism? Ruling the barocaloric effect? Is the spin crossover. It's a completely different mechanism for the barocaloric effect at room temperature. You can turn the page and start discussing a completely new physics. A new physics in comparison with the physics I was discussing previously. So let's erase the board and start discussing a new physics. For this case, let's consider all of this, or most of this. It's better to say most of this because maybe we can find some exceptions. Let's consider 3D ions, 3D for this case, 3D ions, inside an octahedra environment, octahedra coordination. For free ion, these 3D ions, these have five orbitals. For a free ion, these are degenerated. However, when you place these ions inside an octahedra, this environment, this coordination, lifts the degeneracy of energy. Why and how? We can see that these green or blue, these orbitals here inside the octahedra have different shapes. And these shapes explain how the degeneracy is lifted. We can see here these two orbitals that's named as EG. These are aligned along the axis. The consequence of that is that the electrostatic repulsion is much bigger than the orbitals of these three orbitals at the bottom. These three orbitals at the bottom, named as T2G, these three orbitals are aligned out of the axis, and the electrostatic repulsion is much smaller than these two orbitals at the top. The consequence is that these two, the EG orbitals, suffer a penalty in energy. That's the reason these two orbitals are at the top, and these three are at the bottom with an energy gap delta. This picture is very important for the spin crossover. I will explain 2 slides ahead. And the spin crossover is the reason for the barocaloric effects in these materials. So we have the main idea. We have different shapes of the orbitals. The consequence of this different shape of the orbitals is this crystal field splitting delta. It produces, in certain cases, the spin crossover, and the spin crossover produces the barocaloric effect. That's the main way of thinking. Okay. How can you distribute electrons considering this situation? Let's suppose the first situation on the right, I mean the low spin configuration. Let's suppose the crystal field splitting delta that I explained before, much bigger than P. What's P? P is the pairing energy to put two electrons in the same orbital. If this energy, if this crystal field split is much bigger, let's suppose the D4 configuration. We have 4 electrons to fill these orbitals. We have 1, 2, 3, and the 4th electron we would put here in this orbital EG. However, the crystal field splitting is quite high. The energy cost is quite high, and then the system prefers to be at the bottom. The effective spin is 1. You can see here, the effective spin is 1. This is the low spin because the fourth electron goes at the bottom. The second situation is the high spin configuration. The high spin configuration, the crystal field splitting is quite small. The fourth electron goes in the EG orbital, 1, 2, 3, and the fourth electron goes in the EG orbital. This effective spin is 2. You can see the difference here between high spin and low spin configurations, spin 2 and spin 1. Okay. What's the spin crossover? But look here, these cases are extreme cases. Crystal field splitting much smaller and much higher than P. However, what does happen when the crystal field splitting is offered the same order of magnitude of P and the same order of magnitude of external excitation, like temperature, mechanical pressure, radiation. The consequences, the spin crossover. The system changes from high spin from low spin. Usually low spin is at low temperature. The system changes from low spin to high spin across temperature. Change in temperature, increasing temperature, the system changes from low spin to high spin. Increasing temperature, the thermal energy induces this change. And you can see here, for example, for this case, D4, the system changes from spin 1 to spin 2. Okay? It can be induced by temperature, mechanical pressure, radiation, and other kinds of external excitations. And the consequences are change in the magnetization, as I presented, change in the crystal parameters, and several other changes. Okay. What's the possible electronic configurations? D1 does not suffer spin crossover because the first electron can be, the electronic configuration is the same, putting only one electron. D2 also does not suffer spin crossover. D3 either. D4, it suffers spin crossover. It's possible to suffer spin crossover because it depends if the crystal field split is of the same order of magnitude than P, that's the same order of magnitude than the external excitation. Okay? D4, it's possible to suffer a spin crossover. D5, also, it's possible to suffer spin crossover. D6, also, because these are different. The electronic configuration are different. You can see here. D7, also. D9, it's not possible to suffer spin crossover because the electronic configuration is the same. D9 either. And then, to summarize, the electronic configuration that's possible to suffer spin crossover are these one, D4, 5, 6, and 7. Examples, chromium ions that can suffer, chromium, manganese, iron, cobalt, nickel, etc. Okay. Here, it's an example of work that it's an ongoing work. Researchers from State University of Rio de Janeiro are doing a very good job, a very good work on the barocaloric effects on these materials. I'm presenting here ongoing work of we are doing. This I'm presenting, it's a published work. These researchers, they measure in a metal complex, here's the magnetization as a function of temperature. For several values of temperature, the magnetization, you can see here how the transition, this is the spin crossover. The system changes. It's a D6. D6, it changes from, you can think, D6 in a low spin, there are 3 spins up and 3 spins down. The effective spin is 0. It's a diamagnetic.
Mario?
Yes.
You have 10 minutes more.
Okay, thank you. You can think D6, in a low spin configuration, it has 3 spins up and 3 spins down. So the effective spin is 0. So it's a diamagnetic material. When it occurs, the transition for a high spin, it changes for a S equal to 2. However, there isn't interaction, magnetic interaction between the molecules, and the system is paramagnetic. So it changes from diamagnetic to paramagnetic. However, associated with this transition, this spin crossover transition, there is a high chance of volume in the octahedra. And here, for this value of pressure, here in this black curve, it's a spin crossover transition for 0 pressure. Applying pressure, there is another transition in a different value of temperature. Applying another value of pressure, another spin crossover, however, in a different value of temperature, and so on. So the spin crossover depends on pressure. And here, the authors measured calorimetric techniques and obtained entropy as a function of temperature. And obtained, it's possible to obtain, just to make the difference, they didn't present the entropy change. That's our ongoing work to obtain this entropy change and describe the model. How is our model? Here is the entropy. We have introduced one contribution depends on the position, because here the blue circles are low spin molecules, red circles are high spin molecules for a certain temperature and pressure. Changing the temperature and pressure, here is T prime and P prime. Changing the temperature and pressure, it has an entropy, associated entropy. So you have considered this entropy. Here's the spin entropy. It's a textbook for the diamagnetic contribution is 0. So it's the paramagnetic entropy. It's a paramagnetic entropy for the spin. It's a textbook. And there are 2 contributions for the LETs. One in-phase contribution that is the acoustic phonons. These acoustic phonons are the bi-contribution, those phonons oscillating in phase. And an optical branch of the phonons oscillating out of phase. We have considered all of these contributions. And here are our results that I'm not explaining details, only presenting superficially. Okay. And here, the dotted lines, the experimental results came from that reference for 43 and 19 megapascal. And the solid lines fitting from our model. And here the contributions. The solid line here in this picture, figure B, is the same as this one. This orange curve at the top is the same as this at the bottom. With the contributions, here is not Einstein no longer because I changed the model. Here's the that's phonon contribution oscillating out of phase. The spin contribution, that's quite small. And the contribution from the position. You can see here that the phonon contribution is quite high because, in fact, it's a barocaloric effect. The contribution from the LETs is very important because it's a entropy due to the pressure on the LETs. Okay. And to conclude, I have presented two main behaviors for these materials. One regarding the magnetocaloric at low temperatures, there is one open question that is to how to improve the materials to keep improving based on that picture. The main question is there another family to keep improving that magnetocaloric effect at low temperatures? Is there another family? And for the barocaloric effect, it has a huge value of caloric effects, not magnetocaloric, but caloric effects. And it's quite competitive, this material, even in comparison with other magnetocaloric effects. And it's possible to explore further this material for applications. Well, once again, thanks for the committee for inviting me to present this talk. It's a satisfaction to present for people in Latin America and other countries this topic. And I'm available to talk with everybody about this talk, and also by email. And thank you again.
Thank you very much, Mario Reis, for your nice seminar with very good results, scientific results, and very didactically. Well, now I will open a session of questions, and because the difference of time, I will invite the first one is Professor Zhang. Professor Zhang, you can do your questions. Thank you very much.
Hello. Thank you. Thank you, Professor Reis, for a very interesting talk. I'm really sorry that I'm more on metallic materials area. I'm not so familiar with this sort of deep physics of the magnetic physics. But of course, as a materials scientist, I was interested in the applications of such materials. The materials are very interesting because I assume that they can replace the conventional mechanism of cooling by the cycling. So I was wondering the potential of such materials. Are these materials usable now for making freezers or fridges for practical cooling? Can we use such material? Can we use such material for practical cooling now?
Yes.
Yeah.
From what I understood from your question is if it's possible to use these materials for cooling. Am I right?
For practical cooling now, yeah, to make a portable fridge.
Yes. Our research is for optimizing magnetic materials. However, there are several groups producing prototypes. It's not our research to study prototypes and the technologies associated with prototypes for this material. However, there are several groups producing prototypes, and the research about prototypes is quite in advance. There are results quite promising, and there are some commercial devices to produce small cooling to cool wine, and there are some devices already available commercially, but not to in large scale like fridges. But people in producing research for devices are producing a very good research, producing very good results in this direction, producing prototypes in a good way.
Yes, thanks. I have another question. In order to have a good magnetocaloric effect, the MCE, does the material need to have a single phase? This metal complex is a single phase, is that right? So Does it have to be used in a single phase, the material?
Yeah, not necessarily. They are not necessarily. There are studies with composites. There are studies with dual phase materials. There are studies with single phase. Depends on the material, not necessarily a single phase. There are several studies with composites.
Also can become. Okay. Again, I'm sorry that.
No, you are welcome.
Physics on this, yeah.
You are welcome. Thank you.
Technology. Thank you.
Thank you very much, Professor Zhang, for your question. Thank you, Mario, for your good answers. And the next question will be done by Professor Albino Aguiar, professor from Federal University of Pernambuco. Albino, it's your time.
Hello. Can you hear me?
Yes.
Good. Mario, congratulations for the very nice talk. Nice to meet you on the web.
Thank you.
I have a practical question. We are facing now a very huge problem. That is people that work with low temperature physics. Which is the price of helium, liquid helium, or gas. So my question is, do you think there is any chance, by using these materials you talked about, that we can, in the near future, forget using liquid helium or doing research?
I don't think so, because as you saw, the range of temperature of these materials is at low temperature, 2 4K. The proposal is to liquefy not helium, but gas for engines. I mean, gas for natural gas, and not helium, because the price of the helium is not because of the liquefaction, but because it's rare. The region that comes from that U.S., most of the place that it's available is in U.S., only in U.S. I mean, the price of the liquid helium is not of the liquefaction. It's several other reasons that make the helium expensive. Liquefaction is
I agree.
Liquefaction is not the problem.
Liquefaction is cheap. Even we here in the equator, we can liquefy helium if you have the gas.
Yes, liquefaction. The
so
problem
no
is
problem.
to get
if you go to Sahara, you can liquefy helium in Sahara.
Yes.
Plus you have the gas. Yeah?
Yes, the problem is to get the gas.
Yeah, this is the problem. So we have to find, we are scientists, we have to find one way, on materials, perhaps a new material, that will allow us to go to 0K approximately.
Okay, I understand. I understand your question. I understand your question. Now I understand your question. But I think it's not the way, because the proposal here is to use this material to liquefy another one.
Yeah, I understood. Thank you very much.
Okay. You're welcome.
Bye. Isaías?
Okay, thank you very much, Albino, for your question, and Mario also for your answers. And now I will invite the Professor Arturo Martinez from Mexico to ask your question. Arturo? Arturo?
Yes, excuse me.
Okay,
Couldn't
go
find it.
ahead.
Okay. Can you tell me the advantage of these complexes compared to typical alloys for the solid state cooling, please?
Well, several materials, all of the materials have advantage and disadvantage. As I don't know if I'm sharing or not. Am I sharing? Yes. Here is a list of properties that you can see some advantage. You ask for advantage or disadvantage?
Advantage.
Yeah, you can see here advantage. For example, mechanical flexibility, synthesis at low temperature. If you can synthesize this material at low temperature, producing in large scale is a great advantage, because for industry to produce one material in 300 degrees is much better than producing 2,000-3,000 degrees. It's already a great advantage. Compatibility with other materials. However, as other materials, it has problems. For example, the magnetic density is quite low because we have other materials. It's the magnetic centers are diluted inside a lot of non-magnetic materials. So it has advantages and disadvantages. Well, it's a compromise that the community needs to study. But the magnetic entropy change for the barocaloric effect is quite huge in comparison with other materials. Even the magnetocaloric effect at low temperatures is much bigger than other materials.
Hey, Mario. Thank you for your very nice talk.
Okay, thank you.
Thank you.
Thank you, Arturo, for the question. And now we'll have, I should call Professor Peter. Professor Peter, you are here? Okay, thank you.
Hi, thank you very much for the very interesting introduction to this topic. So you presented this graph of how these effects change over time, right, as you progress through these different complexes. So what's the limitation to this increasing that people are working on now? Is that looking at sort of increasingly complicated chains of different structures? Are we looking at different metal ions to improve this magnetocaloric effect?
This picture, you mean? Let me change here.
Yeah. What sort of things do we need to achieve to get into this top right-hand corner, I guess is my question. Is that a case of developing a more complicated chain or like going towards different ions in the structure?
Well, I didn't discuss this topic. I skipped this point. There are some methodologies to achieve the highest entropy change. I don't know if that's the point you meant.
Yeah,
I put it here. To achieve the highest value, the material needs a negligible anisotropy, negligible magnetic interaction, and the smallest ligands. That's the recipe to achieve the highest magnetic anisotropy. It's described in that review article, but I didn't have the time to describe this in details. But this is the recipe to achieve the logarithm of 2s plus 1. That's the main recipe. But from the chemistry point of view, it's not so easy to obtain this material. I do not produce these samples. And my colleagues from the chemistry department, people that are in the lab producing the samples, they say that's quite difficult to manage these rules. But these are from the physical point of view, this is the receipt. But from the chemistry point of view, these are quite difficult to handle.
Okay, thank you.
You're welcome.
Thank you, Professor Peter Newton. And to remember everyone here, Professor Peter Newton will give for us a seminar within 7 weeks. Thank you, Professor Peter, for your question. Mario, now I will call Professor Felipe. Professor Felipe, are you here?
Yeah, thanks. Thanks for your lecture. And what are the reasons of the high performance in the metallic calorific effect in metal complex comparing with other systems?
I couldn't follow. Can you repeat, please?
Yes. What are the reasons of the high performance in the metallic calorific effect with you comparing it with other systems?
Which one you mean?
I don't know what other system you are working in your work.
Well, as I have discussed with our other colleague, there are several advantages and disadvantages. This material, as I described it, it presents a magnetocaloric effect at low, because nowadays, for maybe 10 years ago, it was very common to describe the magnetocaloric effects. However, nowadays, it's usual to study the caloric effects and try to combine magnetocaloric with barocaloric, electrocaloric. People do multicaloric effects, trying to combine all of these effects. It's very common to combine ferroelectric with ferromagnetic to try to optimize the properties of the material. For this material, I have presented the magnetocaloric effects at low temperature and the barocaloric effects at high temperature. So it's a huge amount of information for these materials. For other materials, it's a bit difficult to compare, to make a simple comparison with these materials with others, because there are several kinds of materials. Not only, I know there are standard families like lanthanum, iron, silicon, gadolinium, silicon, German, gadolinium, the pure gadolinium. However, for the last 7 or bit more years now, we are facing several new materials, including these I'm presenting to you, but there are several new families of materials, especially the multicaloric materials. People are doing composites with, like Professor Zhang asked, people are preparing composites with several properties that you can access. For example, the magnetic parts accessing by pressure, by electric fields, and it's not simple to answer your question with so simple like this. So because there are several families emerging in the last few years, you see.
Okay, thanks.
Thank you again, Professor Felipe. Now we have a question from Professor Davi Landinez from University of National University of Colombia, but he is not very well, and he wrote it, and I suppose it is with Ximena. Ximena, can you read the question of Professor David Landinez?
In this moment, we have a question from Professor David Landinez. We only have thanks for all this conference, for an interesting topic that you can hear. And thanks for it.
Okay. Thank you, Ximena. And I'll try to contact again with Professor David. Anyway, now, so let's do next question. Professor Sérgio Conejos.
Here I am. Okay. Thank you very much for your presentation, Mario. Your presentation it was very clear to me. I'm not expert in your field, but I was able to follow your talk. Very nice for that. I have one question for the magnetocaloric effect, because it's interesting the problem here, because you need to have negligible magnetic interactions, but at the same time you need to have high magnetic density. So you commented that the gadolinium is the best magnetic center for this kind of material. But I would like to know what kind of ligands people or material scientists use for materials. I mean the composition of the ligands, because you need to have a good ligand in the sense that the ligand can't be too small, otherwise the magnetic centers are going to interact. So my question is, what kind of ligands people use for synthesizing this kind of materials?
Yes, it's a very good question. It's a bit tricky. I prefer not to say the name of the ligands because I'm not from the chemistry. I can say something wrong if I say the name of the ligands, especially because the words are very complex, and I prefer not to say because I'm not from the chemistry. But it's tricky because we need to make the metal centers as close as possible to decrease the magnetic density. However, without making them interacting. That's the idea. As I explained before, from the physical point of view, it's easy. It's that to say to the people from the chemistry, but when I explain to people from the chemistry, it's hard to prepare. That's the point. It's from the physics point of view, that's the receipt. However, from people in the chemistry lab, it's very difficult to prepare this kind of sample. You can see here, I can show you one example. Here, these are the magnetic entropy chains for only transition metals. And you can see here that average value is around 20 or around here. And you can see there is one result here that's quite above. That's why this result here, the authors could remove the ligands and place one molecule of water. They changed the ligand that was a big molecule and remove and put one molecule of water. and they could change, they increase the density of magnetic density, decreasing the magnetic interaction between molecules, and then improve the results. It's an example to explain why that's the way. And they obtain a quite high result.
Yes, thank you very much.
Okay, you're welcome.
Okay.
Thank you, Sergio, for your question. And now we have more. Now I will open the question from the audience, because this live is send the view for all peoples, of course, from different medias. And the media, one of them can control this contact is James Goodday James from National University of Maior de São Marcos. James, are you here? You have a question from the audience?
Gracias, profesor Isaías. Saludo, profesor Mario. No hay preguntas del público, solo agradecimiento y felicitaciones por su exposición. Gracias.
Okay, James. And from the audience from Colombia, Ximena.
In this moment, we don't have questions from Reis. We only have to say thank you.
Thank you, Ximena. And so I would like to thanks again the news people, the invited speaker here, in the news next speaker, Professor Peter Newton from Cambridge, Professor the editor of the editor Professor Zhang, and I will open opportunity to our speaker send your last consideration, Mario.
Oh, yeah, I'm really surprised about the organization. How broad is this network? It's in fact covers several countries in Latin America. I'm very happy with this organizing, especially if including students. It's very important to include students. Thanks once again for the organizers for this invitation. A good weekend for everybody, and thanks once again.
Mario,
I hope it can be useful for you, for everybody.
Okay, Mario, if you could close your presentation.
Okay, of course.
Just for usual, if possible, everybody can open. Before this, I would like to know that our General Secretary would like to take some words. Luis?
Well, thank you very much, Isaías. Yeah, thank you very much, Mario Reis, for a very nice talk. Just a
moment. I forgot to call Professor José Fermi. Sorry, Fermi. You have a question?
Now, I understood almost everything. Thank you, Mario.
Sorry so much, Fermi.
Sorry for me. Sorry for me. Yeah, sorry for maybe we forgot that. Maybe this was quite long. Yes, what I was saying that unfortunately, Professor Delian Zhang, who is the editor of the Heat Treatment and Surface Engineering, is not present in this moment because he's in China, and in China is nearly midnight now. Well, yes, we also but maybe next time he's going to join us again. But we have here one of the invited panelists, which is Dr. Peter Newton from the University of Cambridge. He accepted to be here today. The previous weeks was Stuart Holmes, also from the University of Cambridge, but today is absent. But I would like to take advantage to introduce, formally, Dr. Peter Newton. He's going to give us a talk during the next month in September. He's going to give a talk. Peter, maybe you let me take advantage to introduce you some of the panelists who has not been at the beginning. For example, Professor Albino Aguiar. Professor Albino Aguiar, let me introduce you, Peter Newton. And also to Mario Reis.
Hello, Luis. Nice to meet you, Peter. Welcome to our network.
Thank you. Good to meet you.
Okay.
Well, okay. Thank you very much, Mario Reis. As I mentioned at the beginning, in the library of the Cavendish Laboratory, University of Cambridge, I came across with your book some years ago. Once I was glancing the new books there on the library, and I found your book.
Yes, I'm right. It has almost 500. I'm writing a book about quantum mechanics. It has 500 pages.
Yes, and then
for the future.
Oh, nice, very nice.
I'll send you a copy.
Thank you very much. And I took one of your, always when I give a talk about magnetism, I take one of your pictures in one of the pages, one of the beginning, when you summarize all the plots there in only one figure. Yeah. Well, thank you very much, Mario.
Yeah.
Well, thank you, all of you. Maybe we can say goodbye to Mario Reis, saying waving hands maybe, and see you next week, which is from the Instituto de Ciencias y Materiales de Barcelona. Will be Bernard Bosso, the next speaker. You are also invited, Mario Reis.
Okay, great.
Professor Bernard Bosso from the Instituto de Ciencias y Materiales de Barcelona is going to give us a talk. Then the week after we give the talk, we are going to have the talk of Ana Palau, also from the Instituto de Ciencias y Materiales de Barcelona in Spain. And the week after will be Professor Felipe Mundaca from the University of Puerto Montt from Chile. Okay, and in September will be the talk from Dr. Peter Newton from the University of Cambridge. Okay, thank you very much. Cheers.
Bye-bye.
Thank you very much. Thank you very much again. Mario, thank you.
Bye. Thank you. Nice talk.
Thank you.
Nice.
Puede cortar la transmisión ya, puede cortar la transmisión. Gracias, Mario.
Recording stopped.
Gracias.
Well, everything is okay. Was okay, I suppose. See you